This is Jack Jackson. In this video we want to try to find the first derivative, the second derivative, the formulas for those, and the equation, the formula for the tangent line to this function here when x equals 1. And our function is f of x equals the natural logarithm of 3x to the fourth minus 2. So if you haven't done this one already, stop the video and compute the first derivative and then come back. Press pause now. Well, the first thing I want to notice is there's this function does have a limited domain. Since it's a logarithm of something, the something that we put in the logarithm must only be positive, not zero, not negative, only positives. So that says the 3x to the fourth minus 2 must be strictly greater than 0. So if we add 2 and divide by 3, that says x to the fourth has to be strictly greater than 2/3. So it says that the absolute, take the fourth root of both sides, we get the absolute value of x on the left, and we get the fourth root of 2/3 on the right. So the absolute value of x is greater than the fourth root of 2/3, which means either x is less than negative, the opposite of the fourth root of 2/3, a negative number, or x is greater than the fourth root of 2/3. So these two numbers are definitely between. This one's between -1 and 1. So negative 0 point something to 0 and 0 point something. So in between these two numbers, there is no, this function is undefined. So there are no points on the original graph, which means the derivative and second derivative must be undefined there as well. So we'll come back to that idea in a minute. In the meantime, we need to do a substitution. So we let u be the 3x to the fourth minus 2. Again, as we work all of these derivative problems, what we want to do is think about what is the outermost function, or what is the last step done in evaluating this function if we plug in a number. Like later on, we're going to plug in x equals 1. First, we'll raise the fourth power, then we multiply by 3, then we subtract 2, and finally take a logarithm. The last step is taking a logarithm. So you want to think of that as the logarithm of u, where u is some other something, in this case 3x to the fourth minus 2. Well, the derivative of log u is 1 over u times the derivative of the u, provided the u is positive. And again, this where u is this thing up here, so u is positive exactly for these x's that we talked about. Okay, so again, the u is the 3x to the fourth minus 2, so notice we use the logarithm rule and the chain rule here. Chain rule is always used in conjunction with another rule. Derivative of this polynomial, 3x to the fourth minus 2, well, the derivative of 2 is 0, but the derivative of 3x to the fourth is 12x cubed. So this becomes 12x cubed over 3x to the fourth minus 2, but with this restriction that x has to be less than negative the fourth root of 2/3 or greater than the positive fourth root of 2/3. If it equals either one of these numbers, then we're dividing by 0, and if it equals something between these two numbers, then the whole, this function, what's interesting is this particular function here would be defined, but the original function is not. So we'll come back to that on the graph in a bit. So let's check our work, and again, we need to only check it for stuff outside of here, but -1 is less than this number, and +1 is greater than this. 0, for example, though, is not in here, and some other values are not in there between these two numbers. Okay, so anyway, as we usually do, we let the original function ln of 3x to the fourth minus 2, we put that in y1. Let y2 be the numerical derivative of y1 with respect to x evaluated at x. Let y3 be our answer, 12x cubed divided by 3x to the fourth minus 2. Notice parentheses around the numerator, parentheses around the denominator. Turn off y1, turn on y2 and y3, check the tables, and we see they're the same. Now notice at 0, we do get an error message on the original function, and we do actually get a number out on this one. So if you actually plug in x equals 0 in this formula, you do get a legitimate number at 0, but that's not a derivative of the original function, because the original function is undefined there. If you plug in 0, for example, 0 to the fourth is 0, times 3 is 0, minus 2 is -2, logarithm -2 is not defined. It does not exist. So the error message is really the appropriate thing. This one really should have an error message there not because of the formula that we put in, but because of this restriction that we're putting here. All right, now let's take another derivative. Well, notice something interesting happened here. We started with a logarithm, and we ended up with a rational function. Now, this one is going to be a rational function, so it's going to use the quotient rule. Of course, pause now and do this next derivative yourself if you haven't done it yet. Okay, hopefully you've done this derivative. So we use the quotient rule, kind of like the last couple of examples. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. The derivative of the top is derivative of 12x cubed is 36x squared. Derivative of the bottom is 12x cubed. 12x cubed times 12x cubed is 144x to the sixth. Distribute, actually I didn't distribute, I left it factored out like that. And notice out of these two terms in the top, two terms are separated by this subtraction right there, right before the 144. And they both have a 36 and an x squared I can factor out. In fact, I'm going to factor out a negative 36x squared. So that means I'm going to divide this out, it'll cancel. This negative here is going to change the signs here. So we get negative 3x to the fourth and plus 2. Negative 144 divided by negative 36 is positive 4x to the sixth divided by x squared is x to the fourth. 4x to the fourth minus 3x to the fourth is 1x to the fourth. We still got our plus 2. We got our 3x to the fourth minus 2 squared in the denominator. And I've still got our negative 36x to the sixth. And we still have our same restriction up here that we had for f prime. We need the same restriction here. Why do we have to write this restriction down? Well, because looking at just at the formula for f prime of x and f double prime of x, they're only undefined at exactly when x equals negative 4th root of 2/3 or x equals the positive 4th root of 2/3. They're not undefined for the things in between, but they should be because the original function is undefined there. So that's what this restriction that we put here and here has the effect of erasing that part of graph between these two, which will actually be vertical asymptotes. Okay, how about the, well, we'll come back to the tangent line in a minute. So notice that the original graph is the blue graph here, and notice this gap in between here, between the vertical asymptotes. And that is the one here on the left, which is quite close to -1, but not quite there, is negative 4th root of 2/3. And close to 1, but not quite 1, is the 4th root of 2/3 is our vertical asymptote here. Between those, there's nothing there on the graph of the function, so there can't be anything there for the graph of the derivative or the second derivative either. Now, let's look at the, now if I were just to graph this without this restriction, okay, and I had to, in Graphmatica, I had to put this restriction on there. I think I had to even actually graph it in 2 pieces and then make sure they were both the same color. But if I didn't put this restriction, then I would get this red graph, but I'd also get some part of the graph between the two asymptotes as well. And that part needs to be erased because of that condition in the original function. In particular, notice the point 0, 0 was a point that would have been on that function of the derivative, on the graph of the derivative, had we not erased this part in the middle. Then the second derivative is right here, and we see its graph in green. Now let's compare the characteristics of these graphs. Now notice that when we're to the, let's say to the left of that first asymptote, so to the left of negative the 4th root of 2/3, okay, then the original graph is here, and notice it's actually decreasing on that interval, which means the derivative should be negative, and that's borne out by this graph here. Okay, and notice, let's see, we should be able to get that from here as well. If you're to the left of there, the denominator is negative, and of course certainly x is negative, so this is negative as well. Okay, so to the left of that asymptote, the derivative is negative and the original function is decreasing. To the right of this other asymptote at positive fourth root of 2/3, the derivative looks like it's positive. Let's see, why would that be true? Well, the derivative, when you're to the right of the fourth root of 2/3, the denominator is positive, and of course over there x is positive, so we got positive divided by positive. That makes a positive value for the derivative right here in red, which means the original function is increasing, which is what you have here. Now, how about the second derivative? Well, the second derivative, again, we're only going to put our attention here. If we didn't have this, if we erase this condition, there would be some graph for the green graph but in this break here. But in fact, there's nothing there for this because of that restriction. Now notice the numerator is 0 when x is 0, but that's something we've eliminated. And this is negative, let's see, x to the fourth is positive, or 0 plus 2 is positive. So other than when x is 0, which has been eliminated, the second derivative is never 0. So that says we shouldn't have any inflection points on our original graph. And sure enough, you can see this first piece is concave down, the second piece is concave down. In fact, the second derivative is always negative. Let's see what happens. Why is that true? Well, for any of these x's you put in, since we got the square, the denominator is positive, and we've eliminated where it's 0, right? And this term is always positive. X squared is always positive. 36 is positive, but we have this negative out here. So the whole thing is negative. So the second derivative is always negative, which means the first derivative is always decreasing where it's defined, which you can see that here and here. And the original function is always concave down where it's defined. And so we get that to work out. Now how about the tangent line? Let's go back and do that. We're interested that we can do the tangent line at any point. I ask you to do it at when x is 1. Let's hope that that's actually in this interval that's defined. Let's check it out. 1 to the fourth is 1 times 3 is 3 minus 2 is 1. Logarithm of 1 is 0. So in fact, 1, 0 is a point on the graph, the blue graph, which is right there. And that's going to be our point of tangency. So that should be on our tangent line as well, which appears to be for that picture. Now, take the derivative, which was this formula, plug in 1 here and here. That gives us 12 over 1 is 12. You see the details worked out there. So the tangent line has a formula of 12 parentheses x minus 1 plus 0, or 12 times x minus 1. And so there we see that the tangent line there is a slope of 12 going through the point 1 and 0. And that is our point of tangency, and the graph and the tangent line follow each other, at least they're close by. Okay, so the next one that I'd like you to take a look at before you watch the next video is, once again, find the first derivative, second derivative, and the tangent line when x equals 1. Graph them together, check them on your graphing calculator, check your calculations, and then also try to examine the graph and see if you can kind of find out where a lot of the interesting features are of that graph. So there's your formula. Go ahead and work that one out before the next video. Come back and we can watch the solution then.